Hello viewers, welcome to my YouTube channel. In today's video, we have this problem that we want to solve together. So it says find a series solution of y prime prime plus y equals 0 about x now equal 1. Okay, so if you're new to this channel, please don't forget to subscribe, like, comment, and share. Okay, so let's dive into the solution. So how do we solve this problem? So we have the general solution for this. Okay, so we assume a series solution of the form y is equal to sum of n from 0 to infinity, then of a of n multiplied by x minus x naught raised to the power of n. So where the absolute value of x minus x naught is less than p, and this is not equal 0. Okay, so and then we already have x naught, which is 1. So they say x naught about x naught equal 1. So what we have now is y equals sum of n from 0 to infinity of an into bracket x minus 1 raised to the power of n. So that's good. So what we need now is y prime prime. So how do we find y prime prime? So if we want to find y prime prime, we must find y prime. Are we together? We must find y prime for us to find y prime prime. Now let's find y prime. It means you want to differentiate this with respect to x just once. That's y prime. So we have y prime will be equal to sum of n from 0 to infinity of a of n. So if you differentiate this, so that will be n multiplied by a of n, then multiplied by x minus 1 raised to the power of n minus 1. Now, if you notice that if you substitute this sum to be, if you substitute n to be 0 right here, so everything here will just give us 0, okay? And then we don't need 0 here, okay? We don't want everything here to be 0. So what it can do, so if n start from 1 to infinity, so what we're going to have here will just be a of 1. Okay, so we're gonna change this summation. It's gonna starting from 1 to infinity. So we have y prime is equal to sum of n from 1 to infinity of n multiplied by a of n multiplied by x minus 1 raised to the power of n minus 1. So you do the same thing to find y prime prime. So y prime prime is equal to, so this will start from 2, n from 2 to infinity. So if we differentiate this, we're going to have n multiplied by n minus 1 multiplied by a of n multiplied by x minus 1, then raised to the power of n minus 1 minus 1, that will be n minus 2. All right, so that's beautiful. So we have y prime prime and y. So we can now substitute y and y prime prime into this equation. Okay, guys, so let's do that. If we do that, we're going to have y prime prime, so which is sum of n from 2 to infinity of n multiplied by n minus 1 multiplied by a of n multiplied by x minus 1 raised to the power of n minus 2, then plus y, which is sum of n from 0 to infinity of an multiplied by x minus 1 raised to the power of n, then everything is equal to 0. Okay, now what I need now is that I want x minus 1 raised to the power of n here, and I already have x minus 1 raised to the power of n. Okay, and then I need this sum. I need them to start from 0. I need both of them to start from 0. Like this, the starting point should be 0, or if this is 1, this is supposed also to be 1. That's the one I want to do. So what am I going to do now is to shift the index, okay, for this. So we shift the index to make the power of x minus 1 the same in both sums. That is the reason why we are shifting the index, to make this power of x minus 1 to be the same. We have raised to the power of n here, so we must also have raised to the power of n here. Okay, so what are we going to do now is to let k be equal to n minus 2. So if k is n minus 2, then n will be equal to k plus 2. Okay, so anyway we see n here, just input k plus 2, and then that's not n. N is equal to 2, so we can find k. So we are going to have k is equal to 2 minus 2, which is equal to 0. So what we're going to have now will be sum of k from 0 to infinity. So n is k plus 2, then multiply by n minus 1. So n is k plus 2. We have k plus 2, then minus 1. Then multiply by a, k plus 2, then multiply by x minus 1, raised to the power of k plus 2, then minus 2. Then plus sum of n from 0 to infinity of a n, x minus 1, raised to the power of n is equal to 0. So what we are going to do now is we can change this k back to n. Since k is just a constant, it's just I mean, just a number, arbitrary value. Okay, so we can change it to n back. So we have sum of n from 0 to infinity of n plus 2, then multiply by, 2 minus 1 will give us 1. So we have n plus 1, then multiply by a of n plus 2, then multiply by x minus 1 raised to the power of n, 2 minus 2 will give us 0. So plus sum of n from 0 to infinity of a of n multiplied by x minus 1 raised to the power of n is equal to 0. That's beautiful, and that's what we want. Okay, this is x minus 1 raised to the power of n. This is also x minus 1 raised to the power of n. So you have the same power. So what we're going to do now is to combine the sums and find the recurrence solution. I mean, the recurrence relation. So if we combine the sum, x minus 1 raised to the power of n is now common throughout. Okay, so what we're going to do now is to factor out x minus 1 raised to the power of n. So we're going to have sum of n from 0 to infinity, then of n plus 2, multiplied by n plus 1, multiplied by plus 2, then plus an, then everything multiplied by x minus 1 raised to the power of n equals 0. Okay, so for this equation to hold for all x in the interval of convergence, so the coefficient of each power of x minus 1 must be 0. Okay, so we must equate this to be 0. Okay, that is, for this equation to hold for all x in the interval given of convergence, the coefficient of each power of x minus 1 must be what? Must be 0. That is, we're going to equate this coefficient to be 0. So if we equate the coefficient to be 0, we're going to have the following. So we're going to have, let's change the ink. So we're going to have n plus 2 multiplied by n plus 1 multiplied by an plus 2, then plus an equal to 0. All right, so let's solve for an plus 2. So if we solve for an plus 2, so we're going to have n plus 2 multiplied by n plus 1 multiplied by an plus 2 is equal to minus an. Then I'll divide both sides by n plus 2, n plus 1 over n plus 2, n plus 1. That's beautiful. So n plus 2 we cancel n plus 2, n plus 1 we cancel n plus 1. So what you have now is an plus 2 is equal to minus an, then over n plus 2 multiplied by n plus 1. So next thing, for n greater than, for n less than or equal to 0. Okay, now what are we going to do now? So we're going to determine the coefficients. Okay, so we're going to determine the coefficients. So we separate the coefficients into even and odd indices, which will be determined by the arbitrary constants a0 and a1. Okay, so let's start when n is equal to 0. What are we going to have? We're going to have a2 is equal to minus a0, then over 0 plus 2 multiplied by 0 plus 1. So we're going to have a2 is equal to minus a0, then over 2 multiplied by 1. Okay, 2 multiplied by 1 is 2, which is also 2 factorial. So this will be minus a0 over 2 factorial. So that is a2. So we are dealing with even coefficients right now. So, and then we know our even number is starting from 0, 2, 4, 6, and so on and so forth. So we are dealing with even coefficients. Okay, so we are done with a0. Now, we are done with when n is equal to 0. Now, when n is equal to 2, what are we going to have? That will be 2 plus 2, that's 4. We have a4 is equal to minus a2, then over 2 plus 2 multiplied by 2 plus 1. So this will be minus a2, then over 2 plus 2 is 4, then multiply by 2 plus 1 is 3. Now, don't forget that a2 is minus a0 over 2 factorial. So we are going to have minus 4 over 4 multiplied by 3 into bracket minus a0 over 2 factorial. Okay, so minus and minus will give us plus. What you have now is a0 over 4 multiplied by 3 multiplied by 2. Okay, multiplied by 1. So which is also 4 factorial. So we have a0 over 4 factorial. That's good. So we are done with when n is equal to 2. Now, what if when n is equal to 4? So what are we going to have? When n is 4, let me go to another page and let's do that. So when n is 4, so we are going to have a6, okay? Because from where we stopped, sorry, this an plus 2. So when n is 4, you are going to have 4 plus 2, which is 6. So we're going to have a6, okay? So we're going to have a6 equal to minus a4, then over 4 plus 2 into bracket 4 plus 1. So which is equal to minus a4, then over 4 plus 2 is 6, then multiply by 4 plus 1, which is 5. And we already have a4, okay? a4 is a naught over 4 factorial, okay? a naught over 4 factorial, so we have minus 1 over 6 multiplied by 5 into bracket a naught over 4 factorial, okay? So this will be equal to minus a naught over 6 times 5. 4 factorial is 4 times 3 times 2 times 1. And this automatically 6 factorial. Okay, so we have a6 is equal to minus a naught over 6 factorial. And so on and so forth like that. Okay, so that's that about the even coefficient. So in general form, general even term. So general even term. So even number is 2 times k, where k is an integer. So we have 2 multiplied by k. Okay, sorry, even numbers. So we have a2k. So it's equal to minus 1 raised to the power of k, then multiplied by a naught over 2k factorial. How do we get this minus 1 raised to the power of k? You can see this is an alternating sequence. Altogether, they are alternating terms. Now you can check. A2 is minus a naught 2 factorial over 2 factorial. Look at something. A2 is equal to minus a naught over 2 factorial. Okay. Next one is A4, a naught over 4 factorial. A4, a naught over 4 factorial. Look at it. A6 is minus a naught over 6 factorial. So definitely a8 will be equal to what? A factorial over 8 factorial. And all together. So next one, you can say a10 will be equal to what? A10 will be a factorial, sorry, minus a factorial over what? Over 10 factorial. You can see. So this is an alternating sequence. So you can see minus 1 raised to the power of k. So when k is 0, you're going to have a naught is equal to what? Everything here will be 0. And then when k is 2, what are you going to have? You're going to have a4. When k is 1, what are you going to have? That will be a2 is equal to minus 1 raised to the power of 1, a naught over 2 factorial. So we have our what? A2. When k is 2, you have your a4. When k is 3, you have your a6. When k is 4, you have your 8, and so on and so forth. So that's how you generalize it. So that's the general even term. So we have a2k is equal to minus 1 raised to the power of k over a naught. Multiplied by a naught over 2k factorial. So let's move on. Let's find the what's it called? The odd terms. So the odd coefficients, for odd numbers start from 1. So n will be 1, 3, 5, 7, and so on and so forth. Those are the odd numbers we are going to have. So, and then don't forget, we already have the general formula for an plus 2. So we know that an plus 2 is equal to minus an over n plus 2, then multiplied by n plus 1. So when n is 1, what are we going to have? We are going to have a3 is equal to minus a1 over 1 plus 2 multiplied by 1 plus 1. So which is equal to minus a1 over 3 multiplied by 2. 3 multiplied by 2 is 6. And this also means 3 multiplied by 2 multiplied by 1. And that's 3 factorial. So you have minus a1 over 3 factorial. Okay? So when n is 3, what are we going to have? We are going to have a3 plus 2. That is a5. Okay? We are going to have a5. So a5 will be equal to minus a3. Okay? Then over 3 plus 2 multiplied by 3 plus 1. Okay, so this will be equal to minus 1 over 3 plus 2 will give us 5. Then multiply by 3 plus 1 will give us 4. Then we already have the value of a3, which is minus a1 over 3 factorial. Minus times minus will give us plus. So we have a1 over 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. That's 3 factorial is 3 times 2 times 1. And this was 5 factorial. So we have a1 over 5 factorial. That's a5. Okay. So if you do that for a6, a7, that's when n is 5. So we are going to have a7 is equal to minus a5. Then over, 5 plus 2 will give us 7. 5 plus 1 will give us 6 multiplied by 6. Then this will give us minus 1 over 7 multiplied by 6. We already have a5. So which is a1 over 5 factorial. a1 over 5 factorial. Okay. So this will be equal to minus a1 over 7 factorial. Okay. So now let's generalize this also. If you look at it, a3 minus a1 over 3 factorial, a5 a1 over 5 factorial, a7 minus a1 over 7 factorial. This is also what? An alternating sequence. Are we together? It's an alternating sequence. And we know that odd number is of this form. N is equal to 2k plus 1. Okay? So where 2k is even, then if you add 1 to an even number, you are going to get an odd number. Are we together? So we have odd number is 2k plus 1. Okay? That's n. So we are going to have a 2k plus 1 is equal to, you can see that is an alternative sequence, minus plus minus plus. So this will be minus 1 raised to the power of k, then multiply by a1. You can see a1 is the common term there. a1 then over 2k plus 1 factorial. That's good. So when n is 0, what are you going to have? You're going to have a1. So, and then that will be, when n is 1, you're going to start from 1, So when n is 1, you're going to have a3. Okay. So when n is 2, you're going to have a5. When n is 3, you're going to have a7, and so on and so forth like that. Okay. So that's the general term for the odd coefficients. Now, since we have the general term for the even coefficient and the odd coefficient, so we can now bring the two together. So we bring them together, we have the following. Sorry, we are almost done. Okay, so we have the following. Let me write it out. So we have y of x is equal to a naught, then multiply by sum of k from 0 to infinity of minus 1 raised to the power of k over 2k factorial, then multiply by x minus 1 raised to the power of 2k. This is for the even coefficients, even terms, plus the odd term, which is a1 multiplied by sum of k from 0 to infinity of minus 1 raised to the power of k over 2k plus 1 factorial, then multiply by x minus 1 raised to the power of 2k plus 1. Now note the power series for cos lambda. You have cos lambda. Cos lambda is equal to sum of n from 0 to, sum of n from 0 to infinity of minus 1 raised to the power of n over 2n factorial multiplied by lambda raised to the power of 2n. So what do you notice here? So your lambda here is just x minus 1. So definitely this will be what? Cos x minus 1. And then same thing for the odd coefficient here. So which is, we know that sine lambda is equal to sum of n from 0 to infinity of minus 1 raised to the power of n over 2n plus 1 factorial multiplied by lambda raised to the power of 2n plus 1. So definitely the second term here is what? Sine x minus 1, since your lambda is x minus 1. So since we have this, we can now join the two solutions together. So we join the two solutions together. So we have y of x is equal to a naught cos x minus 1, then plus a1 sine x minus 1. And that's the general solution to the DE. Therefore, the general solution to the differential equation is yx is equal to a naught cos x minus 1 plus a1 sine x minus 1. All right, so that's the answer to that problem. If you like this kind of video, please don't forget to subscribe, like, comment, and share. So let me just give you an hint to the next problem we are going to solve. We're going to solve the general form of the Mite problem. Okay, so that's what we'll be doing in our next video. Thanks guys for watching. See you next time. Please don't forget to subscribe. Thank you.